Hello, my name is Isabel Duffy, a senior at American Heritage, and I will be presenting my project, the lactase-mediated degradation of low-density polyethylene and polystyrene via invasion and ingestion by Pleurotus austratus. I first developed the idea for this project when I was reading articles about how mushrooms, such as Pleurotus austratus, were being found to grow in landfills, and I was curious about this. In addition to that, I read several papers about how enzymes were being used to degrade plastic and make them hydrophobic. So to begin with the biodegradation approach, using enzymes to effectively break down plastic makes them hydrophobic. I used lactase, a copper-based enzyme that oxidizes phenolithic substrates and creates active radicals that are able to break down the carbon-carbon bonds in plastic that make the plastic hydrophobic. In addition to that, Pleurotus austratus, seen here in the photo, is a wood-rotting mushroom that contains additional enzymes that break down the polymers in plastic and have been found to use them as an energy source. So that is what I was testing in this experiment. The experimental design, I asked one question: to assess whether a two-step approach to degradation can accelerate the breakdown of plastic compared to the 400 plus years seen in nature. The materials I used were low-density polyethylene and polystyrene sheets, most common types of plastic found in landfills, the enzyme, the mushroom, and a scanning electron microscope imaging equipment. So the first procedure was lactase application. 5 milliliters of a lactase solution was applied every 5 days for 0, 15, or 30 days, my variables. And then there was also a fungal treatment, where plastics were placed face down on sheets of agar covered in Pleurotus austratus, so that the fungus could break down the plastic. As we see here in the photo, one fungus was actually able to eat a hole through the plastic and come out through the other side. Next, weight loss. One of my assays was the weight loss of both plastics with lactase enzyme application and fungal application. And we can see here it was weighed every 5 days, and there's 3 groups. The same thing can be seen with continued Pleurotus austratus exposure. We see a trend: as more lactase enzyme in exposure happens, more weight loss occurs. The same thing can be seen when I measured density loss. That density loss increased as more enzyme and fungal exposure occurred. Now, at the end of the 30 days of lactase application and fungal exposure, I brought the plastic sheets to the scanning electron microscope, where I was able to see close the fungal and lactase degradation as it ate through the plastic. Conclusion: there is a significant potential of combined enzymatic and fungal approach for plastic degradation. The control groups with no enzymatic or fungal exposure showed no signs of degradation, while the other variables, such as 15 days of lactase exposure and 30 days, did show signs of degradation. For future research, I would like to focus on the industrial scaling of this method in order to bring more plastic degradation, because it is low cost and eco-friendly, making it a sustainable method for the future. For error analysis, there was weight measurement error test, enzyme activity variability test, and a Friedman test in order to measure statistical significance. Thank you.